Hello everyone, and welcome back to the channel. I'm Lena, an AI consultant working as a freelancer in partnership with Weaviate Digital Marketing Company. Today, we're diving even deeper into a cornerstone of modern AI technology: vector databases. If you've ever wondered how systems like ChatGPT, recommendation engines, or semantic search platforms find relevant information almost magically fast, then this video is for you. We'll explore what makes vector databases unique, the techniques behind how they store and index data, how they integrate with large language models and retrieval-augmented generation systems, and much more. By the end, you'll not only understand the what and how, but also get a sense of the why. Why vector databases are redefining how machines process meaning and context. In this video, we are going to cover some of the important concepts of vector database. Difference between traditional database and vector database. Vector storage and indexing techniques, HNSW, IVF, PQ. CRUD operations in vector databases. Integrating vector databases with LLMs and RAG, Retrieval-Augmented Generation. Comparison of popular tools, Pinecone, Weaviate, Milvus, Chroma, FAISS, Qdrant. Performance optimization and scalability. Security and compliance considerations. All right. Let's dive in and start with the difference between traditional database and vector database. Traditionally, the databases store structured data like rows, columns, numbers, categories. But AI models don't think in spreadsheets or traditional way. They understand the world through embeddings and high-dimensional numerical representations of the meaning. A vector database is built to store and search through these embeddings efficiently. Instead of asking for an exact keyword, a vector database finds results that are close in meaning rather than exact text matching. For example, if you query artificial intelligence, the database can return documents about machine learning or neural networks because their vector representations are nearby in space. The magic lies in how these vectors are stored and indexed. Let's unpack three major techniques of indexing in vector storage. These popular indexings are HNSW, IVF, and PQ. Let's start with HNSW indexing, which is known as Hierarchical Navigable Small World. HNSW is one of the most popular graph-based indexing methods. Let's discuss how it works. It builds multiple layers of a navigable small world graph. High-level nodes connect broadly across the graph, while lower levels focus on finer details. During a search, the algorithm starts at the top layer and quickly narrows down to the most relevant nodes below. This approach allows lightning-fast approximate nearest neighbor searches with remarkable accuracy. The next indexing is IVF, which is known as Inverted File Index. Let's see how it works. IVF divides the entire vector space into clusters or cells. When you insert a new vector, it is stored in its nearest cluster. At query time, instead of searching through all vectors, the system only searches the few clusters closest to the query vector. This method greatly reduces computation and speeds up retrieval. The next indexing is PQ, which is known as product quantization. Let's discuss how it works. Product quantization compresses vectors into smaller binary representations. It divides each vector into subvectors, quantizes them individually, and stores compact codes. This technique allows huge datasets to fit into memory while maintaining acceptable precision. It's excellent for large-scale systems like recommendation engines with billions of embeddings. By combining these methods, vector databases can achieve both speed and memory efficiency. I hope you are clear with the concept what we discussed so far. Now, we are going to discuss on CRUD operations in vector databases. In traditional databases, CRUD stands for create, read, update, and delete. The same principle applies here, but with embedded vectors. First, let's discuss about create in vector database. When you add data, say a paragraph or product description, an embedding model first converts it into a vector. That vector is then inserted into the database along with metadata like an ID or category tag. Next, let's talk about read in vector database. Reading means performing similarity searches. You send a query, transform it into a vector, and retrieve the closest embeddings using distance metrics like cosine similarity or Euclidean distance, which we discussed in our previous video. Next comes the update in vector database. When underlying data changes, you can re-embed and update the corresponding vector entry. Some databases support partial updates. Others require reinsertion. Last but not the least, let's talk about delete in vector database. Finally, you can delete vectors by ID. Efficient indexing ensures that deletions don't degrade performance over time. CRUD operations are the backbone of managing embeddings dynamically and essential for evolving datasets in AI-driven systems too. Hope things are good, and I got the understanding that you are catching up. Now we come to one of the most exciting applications, that is integrating vector databases with large language models in a RAG, or Retrieval-Augmented Generation architecture. Let's understand how it works. 1. A user asks a question to an LLM. 2. Instead of letting the LLM rely solely on its internal memory, a vector database retrieves relevant context from an external dataset. 3. That retrieved context is passed back to the LLM to produce a precise, up-to-date, and grounded response. For instance, if you're building an AI assistant for healthcare or finance, you can store verified documents as embeddings in a vector database. When a user asks a question, the system fetches only relevant data and feeds it into the model. This approach greatly reduces hallucinations and enhances the model's factual reliability. Platforms like Pinecone, Weaviate, Milvus, and Chroma make this integration seamless through API-level connectors to frameworks like LangChain and Llama Index. Now let's discuss about the comparison of popular vector database tools like Pinecone, Weaviate, Milvus, Chroma, FAISS, and Qdrant. We will discuss one by one. To start with Pinecone Vector Database, this stands out as a fully managed cloud-native service that offers easy scalability and seamless integration with retrievers and large language models, making it perfect for production-grade AI applications. The next vector database is Weaviate. Being open source and schema-driven, provides built-in machine learning modules ideal for creating semantic knowledge graphs, where relationships between data points matter. The next one is Milvus Vector Database. It is a high-performance enterprise solution, written in C++, supporting various indexing options such as IVF, HNSW, and PQ, which allows it to manage massive datasets efficiently. The next one is the famous Chroma Vector Database. It is lightweight and Python-friendly, making it a great choice for small-scale projects and rapid prototyping of retrieval-augmented generation systems. The another famous vector database is FAISS. This database is developed by Facebook AI, is not a database server, but a high-speed vector similarity library that scholars and engineers use to experiment and optimize vector search locally. Final ones is Qdrant Vector Database. This database built in Rust combines speed with flexibility, supporting payload filtering and hybrid search across vector and text data, making it suitable for use cases requiring both structured and semantic matching. Together, these tools cater to different needs, from academic experimentation to enterprise, scale AI deployments, balancing performance, control, and ease of use. Each tool comes with trade-offs. For experimentation, FAISS or Chroma might be enough. For serious deployments, Milvus, Pinecone, or Qdrant offer robust and scalable solutions. So far, we have discussed a lot of important concepts in vector database. I think it's time for us to discuss on performance optimization and scalability in vector database. Let's dive in. Vector databases must handle massive volumes of high-dimensional data, often in real time. Optimizations typically target 3 areas: index tuning, scaling, and hardware utilization. Let's understand one by one. Index tuning means choosing the right index type for the data scale and search precision. For instance, HNSW is great for recall-sensitive tasks, while IVF-PQ works for memory efficiency. Next is distributed scaling, which means systems like Milvus shard vectors across nodes and parallelized search. This linear scaling keeps latency low even as data grows. The last one is hardware acceleration. It is like modern systems leverage GPUs, SIMD instructions, or vectorized libraries to accelerate similarity computations. Caching frequent queries and pre-computing clusters can further enhance performance for high-traffic applications. Let's discuss about security and compliance considerations, why it is critical. As vector databases store semantically rich embeddings derived from real-world data, security and compliance are critical. Encryption in transit and at rest prevents data leakage. Access control and role-based permissions ensure only authorized queries can access sensitive information. Data governance tools help trace embeddings back to their source to comply with standards like GDPR or HIPAA. You must also consider data anonymization, since embeddings can sometimes leak clues about user content. Responsible storage and lifecycle management of embeddings are vital for compliance and trust. I hope you are clear with the clarifications on security and compliance. Let's wrap up with a real-world use case and summary. Imagine you're building a customer support chatbot. You embed thousands of documents from internal knowledge bases, FAQs, and conversation logs into a vector database. When a user types a question, the query is turned into a vector, matched with similar entries, and the LLM uses the retrieved text to form an accurate answer. That's vector search and RAG in action, delivering precision, relevance, and contextual understanding. Ending at scale. To summarize, vector databases store meaning, not just text. Techniques like HNSW, IVF, and PQ keep searches fast and efficient. CRUD operations maintain flexibility. Integration with RAG transforms static models into dynamic problem solvers. Tools like Pinecone, Milvus, and Qdrant each cater to different needs. And finally, performance tuning and security ensure real-world reliability. Thank you for watching. If you found value in this video, consider liking it, subscribing to the channel, and sharing it with others who might benefit. We'll soon be releasing more such videos on AI, machine learning, and vector databases. So stay tuned and keep growing your knowledge with us. Until then, take care and keep exploring the exciting world of AI. Thank you once again.